Green.
Thank you very much for the invitation to speak. Claude suggested that I talk about this topic. Before I forget, let me just say from the very beginning that an L function is a more general version of a zeta function. So the words zeta and L are sort of mixed up historically, and I will flip between the two. Okay, so let me begin with a bit of provocation, and I'd like to raise a completely crazy question, which is there a formula for period integrals such as the ones we've seen in this conference? So here, omega is an algebraic differential form on an algebraic variety defined over the rationals, let's say. And sigma is a chain of integration whose boundary is contained in some algebraic subvariety. So this doesn't seem to make much sense, but it's a theme that recurs in this area and amplitudes generally, where we have a quantum field theory or a string theory, and we want to be able to predict the types of numbers and functions that are going to occur in it by pure thought. Okay, so what possible sort of answer to this question could make any sense at all? So let me begin with a very classical example. Here's a period integral. Everything is very algebraic, from 0 to 1 of this 2 form. And it has a formula which is given by the product over all primes of 1 minus 1 over p squared inverse. So that's what I mean by a formula for this integral. And I think we all know how to do this, and that's because the integral I is simply zeta 2, which is an easy exercise and was known by Leibniz in the 17th century. And zeta of 2, or the zeta function, the values of the zeta function are defined to be infinite products over primes. So here's a more non-trivial example. Oops, sorry. So up here we have now a triple integral in 3 variables, x, y, and z, of this rational, this quotient of polynomials. And many of you will immediately be able to recognize the physics lurking behind this. You'll be able to spot some secret Semanzic polynomials. I think this integral actually may have occurred in one of David's recent talks, perhaps not this one, but a recent one. And you can show that this integral also has a formula. It's 4 times pi square root of 15 times LF of 2. So L here is again an L function. It's defined by an infinite product over all primes of some very simple factor here. Well, this p over 15 here is a Legendre symbol. And AP is an integer, which is very mysteriously related to the number of solutions to this equation, which is the denominator, over finite fields FP. So something very subtle is happening here, is that this product actually only converges when the real part of S is bigger than 2, but we need to evaluate it at S equals 2, which is a priori not a legitimate point. So something very subtle is happening here. And in fact, this example that you may know very well, and we kind of take these things for granted, is actually illustrates some of the deepest and most celebrated results in number theory over the past few centuries even. So it illustrates some of the really big theorems in mathematics. Okay, so this brings us to the subject of L functions. There's a very deep and very conjectural program that goes back all the way to Euler. And the list of names of people who've spent their entire lifetimes working on this would fill an entire slide. So I've been very brief here. And very roughly speaking, is to look at L functions and interpret their values as periods. So occasionally, by accident, periods will happen to be values of L functions, and we've seen many examples of this. However, it will be exceptionally rare for a period integral to happen to be the value of an L function. Clearly, if we take two numbers with infinite products and we were say to add them together, that's going to destroy the infinite product structure completely. So that's something we're going to have to give up. And only very special periods have any chance to be L values. So I've put a little footnote here. Those of you who know about motivic periods, you can decompose a motivic period in complete generality into an F alphabet. So many of you are familiar with this in the case of multiple zetas. A necessary condition is that your period should be a single letter in that F alphabet. But that's nowhere near strong enough. You need many more conditions to have any chance of being an L value. Okay, so that's not much help to us. And the question I want to raise then, which is a bit wacky, is whether there could possibly exist mixed L functions whose values actually capture all periods. So I would love it to be the case that any period could be the value of something yet to be defined, which is a mixed L function. Now, the problem with this very heuristic and very speculative picture is that both sides are very mysterious. The left-hand side, well, there is no definition, certainly no agreed definition of what a mixed L function should be, let alone whether it should exist at all. And the other problem is that, you know, we can write down lots of random periods, but there are very few whose structure and geometry we really understand. So there's not much evidence to go on. And so what I'm going to do in this talk is give a very tentative first definition of what a mixed L function might be. This is by no means the final word on this question. The theory of L functions took 300 years of trial and error to develop. This is just a first step towards this very, very conjectural picture. But in any case, what I will do is define some new objects, and these new objects will in fact be connected to a lot of interesting mathematics, which relates to some of the topics that have been studied in this conference, and that's what I want to explain. Okay, so a quick plan. So the first part is going to be a very rough review of the classical theory of L functions. Many of you know this very well already, so please indulge me. So the setup here is we want to consider not just any old L functions. There are plenty of L functions that don't fit in the context I want to consider. So what we like to consider what are called motivic L functions. I won't say what that is, but they come from geometry in some sense. There are plenty of L functions that don't come from geometry. But the ones that come from geometry are Dirichlet series, so sum an over n to the s, with the property that they have an Euler product, a factorization over all primes, where each factor is the inverse of essentially a polynomial in p to the minus s. And that polynomial is related to geometry in the sense that it very approximately relates to counting points on algebraic varieties over finite fields. More precisely, it's related to the determinant of Frobenius on the L-adic cohomology. But let's not worry about that. So in any case, we have a very large supply of very natural Dirichlet series which come from algebraic varieties. And what you can do is complete it. So the L function on its own doesn't have great properties, but you complete it to a function called lambda. And you do that by multiplying by a certain number of gamma functions here, which are called gamma factors. You might want to multiply by some power of pi, and then some integer to the minus s over 2. So n here is called a conductor, and it contains information about primes of bad reduction. The gamma functions here well, this factor here is entirely determined by some integers ni, and they can essentially be read off the Hodge theory and the action of complex conjugation on the cohomology of your variety. So Serre gave a very precise recipe for how to construct this completed L function from your motivic L function. So once you've completed your L function, you conjecture that the function lambda has a meromorphic continuation to the whole complex plane. In fact, you conjecture a lot more. You can say something about where you expect the poles to be. It needs also to be bounded in vertical strips. There's a whole bunch of things that are conjectured, which I will gloss over. And then there should be a functional equation. So here I've made an assumption. I've written here self-dual case only. In general, if you do lambda m of, if you look at this equation, what happens is you get different L functions appearing on different sides of the equation. You get what's called the dual motive. But let's not worry about that. For most of the talk, I'm just going to look at this case where you get the same L function on both sides. So here we have lambda of s equals in a number which is necessarily plus or minus 1 of lambda of w minus s. And these conjectures are incredibly deep and incredibly difficult, but in all the cases that we're going to look at, very simple and very classical L functions, these will all be theorems. And then the matter in this subject is that the values of L functions at integers are very interesting and encode arithmetic information. So there are basically so this is the sort of the condensed, very condensed version of the theory. There are essentially two different types of values of the L function. Let me ignore the fact that, of course, these functions can have poles. They can vanish as well. When they vanish, you want to take derivatives, but let's ignore all of that. Roughly speaking, there are two types of values you're interested in: the critical values and the non-critical values. So the critical values are the ones where the integers n, where n is neither a pole of the gamma factors. So recall the gamma factors are here, and we know exactly what the poles of gamma are. So they're not a pole of the gamma factors occurring in here. Neither are they a pole of the gamma factors occurring in this L function on the other side. So that's a critical value. It doesn't mean that the integer is inside the critical strip. Okay, that's an accident of vocabulary that the word critical is used in both contexts. And we'll see an example where critical here does not imply being in the critical strip. So Deligne made a conjecture about critical values. And Beilinson later made a conjecture about non-critical values, which are all the other values. But in both cases, it's expected that the values, the integers of these L functions are periods. Okay. So let's do some examples. So amazingly, in this theory, that if you take the trivial motive, which is just a point, the cohomology of a point, you might expect you just get the function 1 or something, but you don't. You get the Riemann zeta function. So the most trivial possible L function is the Riemann zeta function. And you can think it's the sum of 1 over n to the s, as we all know, and it has a factorization, of course, only for the real part of s sufficiently large. The completed version was called Xi by Riemann, and it's a power of pi times a gamma factor times zeta of s. And in this case, the functional equation relates s, Xi of s, and Xi of 1 minus s. And in this situation, as we all know, it's very easy to show that the zeta values are periods. They're given by this very explicit integral. And critical in this case, if you sit down and work out what critical means, in the range when n is bigger than 1, it means that n is an even integer. And as we all know, there's a dichotomy. There's a massive difference between the even values of Riemann zeta and odd values. And Deligne's conjecture tells us about the critical values. And in this case, it predicts a theorem which was known long before by Euler, that the even zeta values are proportional to an even power of 2 pi I, which indeed they are. Beilinsen's conjecture about the odd zeta values is much more subtle, and I wouldn't be able to explain it without spending a very large amount of time on background and speaking about motives and extensions and so on. Here's another example that's come up quite a lot in this conference. Let's just take a modular form for simplicity of level 1, but it works in any level. So everything on this page was worked out by Hecker a very long time ago. So F, the modular form, has a Fourier expansion, sum an q to the n, where q equals e to the 2 pi I tor, and tor is in the upper half plane. And we'll assume for now it's an eigenfunction for Hecker operators. So then the L function is the sum of an, it's the same Fourier coefficients here, over n to the s. So it's just the Dirichlet series given by this. But there's a subtlety here, which may look like a typo, but it's not. And that's that you throw away the first Fourier coefficient a0. The L function only involves the Fourier coefficient starting from 1, which seems quite strange, but we'll see why later on. In fact, that definition works for any modular form, even if it's not a Hecker eigenfunction. But when it's a Hecker eigenfunction, then it has a factorization into this product. Okay. So this is all Hecker's work. The completed version, lambda, is 2 pi to the minus s gamma s L f of s. And you may be wondering why this might look a little bit different from the gamma factors I had before, but don't forget that there's the duplication formula for the gamma function, which expresses a gamma function, so gamma of 2s as a product of gamma s over 2, gamma of s over 2 plus 1. So one should really think of the gamma factors here actually as a product of 2 gamma factors. And in general, the number of gamma factors is called a rank. So these are really rank 2 objects. And so Hecker also proved that the functional equation is this one here. So the weight is, there's a sign, and the axis of symmetry is 2w minus, there's a fraction 2w minus s. Okay, very classical. Oops. Okay, so now I want to tentatively feel my way towards possible mixed L functions. As I say, there's no definition out there, and there's no at most noises in the literature that such a thing might exist. I'll say a bit more about that, but there isn't. It's not clear whether such a thing should exist at all. But if it did, we would want it to be related to periods. So I'll start with some caveats of what the definition is not going to be. So the first class of mixed periods that aren't sort of classical L values that we already know about, that we'd want to consider are multiple zeta values. So I think everybody's seen these before. They are periods of possibly the simplest possible types of mixed motives we know about, mixed Tate motives over the integers. And so any theory that we come up with had better capture these numbers, otherwise we're in all sorts of trouble. So we want to get multiple zeta values as values of our mixed L functions, at the very least. And a naive answer to this would be just to simply do like the Riemann zeta function and replace the indices with an S, and look at what's called a multiple zeta function. Now, in fact, these do have a meromorphic continuation. I think that was proven by Zhao. But they have poles along infinitely many hyperplanes. And that is bad. So I put, I'm sorry, this bad exclamation mark reminds me of a sort of Donald Trump tweet. And I apologize for that. I've got a few exclamation marks throughout my lecture. So if someone could do a little cartoon Donald that we could put in the corner with good or bad exclamation mark, then it would spice up the talk with some value judgments. But in any case, I would like to think that this is not the sort of thing that we want to consider. And there is no known functional equation for these as of yet. So they are not going to be examples of the mixed L functions I want to consider. This is not the definition, okay? Here's another thing you might do along the same sort of line of reasoning. You might want to just try and define a double L function. Take two Dirichlet series, L1 and L2, with coefficients an and bn, and consider this sort of nested sum, this nested Dirichlet series. So people have done this. There's a literature on this. This is not the definition I want to take in this talk, but it does happen. There are certain particular circumstances where the definition I'm going to give happens to give formulae of this type. And this occurs, for example, if L1 and L2 correspond to Hecker eigenforms and S1 is an integer. So sort of by accident, in this case, I can actually prove that this function has an analytic continuation and some kind of functional relations. But that's just an accident. Okay, so that's not what the definition is. Now, what is the definition? So the idea is to use integrals rather than sums, and follow Docchester and Zagier, who use this technique for computing L functions to very high accuracy. And you can write, we're going to assume all the functional equation and analytic properties of lambda and write it as a Mellin transform. So it's an integral from 0 to infinity of a certain kernel theta, t to the s dt over t. And this function theta, you can write it down. It's just some an, these are the same coefficients that occurred in the Dirichlet series, times some function phi. And this function phi is typically an exponential. It's given by some inverse Mellin transform of the gamma factors. So the great thing about this is that once you've got, if you're looking at L functions with a certain type of gamma factor, you just compute this function phi once and for all, and then you've got a universal recipe for all your L functions of that type, and you can just write down these theta series. So now what happens is that this function theta 0 can now be completed into theta, what I'm going to call theta m, by adding an extra term, theta infinity, which is just a polynomial. So you correct it with a polynomial, and then the completed theta satisfies this very beautiful function equation. But when you inverse t, you get t to the w. That's the same w that occurs in the functional equation for lambda, and the epsilon is the same sign in the functional equation, times theta. Okay, so some examples. For the Riemann zeta function, we have a classical Jacobi theta function. So sum of the integers e to the minus pi n squared t squared. And this you can view as 1 plus all the bits that have a non-trivial dependence on t. So the theta infinity t is this is a polynomial, it's just 1, and the rest decays extremely rapidly as t goes to infinity. And that means you can get very fast conversions. And the functional equation here is this one. In the second example, we had a modular form. The theta function is essentially gives you back the modular form. And when it's a cusp form, there's no zeroth Fourier coefficient, so there's no divergence at infinity. Okay, theta infinity is 0. And this is the function equation, which is the same one we had before. Okay, so what's the definition of a mixed L function? So we're going to take now a bunch of theta functions, theta 1 up to theta r, and we assume they satisfy a functional equation like this, and that they can be decomposed into an infinite part, which is just a polynomial in t, and the rest, which is going to go to 0 exponentially fast at infinity. And then we can define a mixed L function, tentatively, to be the iterated integral of all of these theta functions times a Mellin variable t1 to the s1 minus 1. So it's an iterated Mellin transform. This may diverge, so we regularize at infinity. And there's a very precise prescription for doing that, which is completely explicit. So in the case of a single function, this regularization at infinity means that you just integrate, you throw away the infinite divergent part. You just keep the exponentially decaying piece, and you integrate that from 0 to infinity, and that gives you back Hecker's original definition of the L function. And I've written here that it's strange. And the reason it's strange is because if you go back to this formula, in the case R is 1, it's completely obvious that the functional equation of theta is equivalent to the functional equation of lambda. If you know something about tangential base points, then it's obvious. But in this picture with theta 0 doesn't satisfy any particularly nice functional equation. It's quite horrible. It's quite surprising that actually the L function, the functional equation of lambda is equivalent to the functional equation of theta. So already in the case R equals 1, this tangential base point business explains something. Okay, so in the case R equals 2, we've got a double integral. Here I've spelled out the definition. If you work it out, and this can be done completely explicitly, you get these completely explicit integrals. There's 2 of them, in fact. And you'll notice that in the upper variable is t2, we've got a theta 0, and that's the one that tends to 0 exponentially fast at infinity. So that's going to enforce the very rapid convergence of these integrals at infinity. So this theta 0 here and here are going to crush this integral and make it really super fast convergent. Great. So here's a theorem that's, I'm sure, obvious to many of you who know about iterated integrals. It's not a very difficult theorem at all. That this multiple mixed L function has a meromorphic continuation to complex plane in R variables with poles along only finitely many hyperplanes in the SI. And you can write down what the poles are and what the residues are and so on. It has a functional equation. So now if you take these R variables S1 up to SR and switch the order and flip them, WR minus SR up to W1 minus S1, then you get this functional equation. And also there's a shuffle product formula. So if you multiply 2 such mixed L functions, they are a sum of other mixed L functions. So they form an algebra. Okay, so there's a definition for what it's worth. I'm not claiming that it's necessarily the be all and end all or the right one in any sense. But I think it does the job in some situations. So that's what I want to discuss now. And the challenge is whether we can relate these to periods in an interesting way. So the first question is, like, what values are we going to evaluate these L functions at? And the best possible thing, the most cautious thing one could do is to take all the SI to correspond to critical values of the corresponding L function. So we had these R theta functions, each of them correspond to an L function, and Deligne defined what it meant to be critical. So we want all the integers to be critical, and that's what I mean by totally critical. So we get a bunch of numbers. So what can we say about these? So the first example is going to be the case of modular forms, just of level 1, but it could be any level. So in level 1 for the time being, if we take F1 up to FR Hecker eigenforms of weights W1 up to WR, then the multiple L function satisfies this functional equation. And the totally critical values, in this case, are just the integers that are completely inside this critical box. So it's not a critical strip now, it's a critical box because it's higher dimensions. So you look at all the values within this range. They're strictly inside the box. And in fact, Manning wrote down the definition of these L functions a while ago. In fact, in the case where they're cusp forms, so there's no regularization to be done. And in this case, you can show that the values are indeed periods. They're periods of the relative completion of the fundamental group of a modular curve. So in more sort of layman's terms, they are iterated integrals of modular forms, of sections of certain algebraic bundles on modular curves, and they're absolutely periods in the sense that we would want. So that something certainly works in that situation. Now, a very recent theorem by a PhD student of mine who's just completing at the moment, Alex Saad. It's a very beautiful theorem, and he proved that all multiple zeta values can be expressed as linear combinations of iterated integrals of Eisenstein series. Okay, so this is subtle because there are many iterated integrals of Eisenstein series which are not multiple zeta values at all. You can get non-critical values of cusp forms. So the proof is very beautiful. It's rather tricky. But what it implies is that we can get all multiple zeta values can arise as the totally critical values of these mixed L functions occurring, coming from Eisenstein series. So here's an example. Zeta of 3 is, as I'm sure many of you know very well indeed, zeta of 3 is an Eichler integral of an Eisenstein series of weight 4. I think this goes back even to Ramanujan. So that's a prototype, and Alex has shown that this is true for all multiple zeta values. So the first test has been passed. We have managed to construct all periods of mixed state motives over Z, also known as multiple zeta values. We have managed to capture them as totally critical values of mixed L functions. So that's a bit of hope. Okay, so modular forms were maybe tricky, so let's step back a bit and go back to the trivial motive and see what this definition gives. And already it's surprisingly interesting. So I remind you that the trivial motive, which is just a point, it's got no geometry at all, a point already generated the Riemann zeta function. And the Mellin transform of the inverse Mellin transform of the Riemann zeta function was this Jacobi theta function. Okay. So let's take iterated Mellin transforms of this Jacobi theta function. And you could call this function the multiple Riemann psi function, because in the case r equals 1, it gives the function that Riemann defined. And it satisfies this function equation here. Psi of S1 up to SR is psi of 1 minus S1, 1 minus S1 minus S1. And now if you was thinking along the lines of the previous slide, where the totally critical values were the ones inside, strictly inside the box of the function equation, you'd be panicking because there is no integer within that's within the box. There's no integer strictly between 0 and 1. So it looks like there's nowhere interesting where we could evaluate this function. And I'm going to come back to that in a little bit later. But don't forget that critical in the case of the Riemann zeta function does not mean inside the critical strip. It means being positive even or negative odd. So totally critical means that the positive, we should look at the arguments where all the SI are positive even. So the question is, like, what can we say about the values of this function for even SI? And we cross our fingers and hope that they're periods. And let me just focus on the case r equals 2, which is rather nice because here's the function equation and here's the shuffle product formula. It's a rather nice little set of properties. You can also show that the residues of these functions along hyperplanes give back the classical Riemann psi function. So in fact, in general, if you look at these totally even values, they can always be written in terms of what I call multiple quadratic sums. So I only wrote down the case r equals 2 here, but then they're nested sums, a bit like a multiple zeta value of, now instead of putting an integer to a power, you have this quadratic term, k1 squared plus k2 squared. And in general, you'd have k1 squared dot 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 up to kr squared. These things turn up a lot in study of lattice sums. They're connected with some questions various questions in physics. In this case, you can show that this double psi function in 2 variables is something very, very simple. It's just a Mellin transform of a real analytic Eisenstein series. And real analytic Eisenstein series we've seen a lot because it comes up all over the shop in string perturbation theory, so it's been in many of the talks already. And it's a really fun exercise to check that the two function equations I wrote down here follow from two properties of the real analytic Eisenstein series: its functional equation and its modularity. And it's a very, if you knew this definition, this formula in advance, you'd very, very easily deduce these two formulas. It's quite fun. In any case, if we put SI to be integers, we deduce that the totally even values are Eichler integrals of not real analytic Eisenstein series, but holomorphic Eisenstein series from I to infinity. Okay, so if I were to integrate from 0 to infinity of a holomorphic Eisenstein series, I would get a power of pi, or I'd get an odd Riemann zeta value. But here we're going to integrate from I to infinity. And what that means is that these numbers are related to iterated integrals on this complex multiplication elliptic curve, whose period lattice is the Gaussian integers. So it's related to, you get L functions of Grossen characters of this elliptic curve showing up as periods occurring in this multiple Riemann psi function. So we're in business here as well, and maybe it's not surprising that if you look at this formula that you should get something to do with Gaussian integers. Okay, so that one works as well. Here's something I'd like to put out there that generalizes the two previous examples. So it's what I'd like to call multiple Jacobi values. So we saw that the Riemann zeta function, just going back again, the theta function was just one of Jacobi's theta functions. Well, why not consider all four of them? So here they are. They're the theta null values. They go back a very long time. So now we have three theta functions. There's a little caveat here, which is that they're not self-dual. So if you look at theta of 1 over t, that may be related to one of the different theta functions. So I didn't talk about that. I assumed self-duality at the beginning, but this is absolutely no problem. And it's very, very easy to deal with. Another issue is that these actually have half integral weight. So the sort of divergence at infinity is not a polynomial in t, but you may get something in square root of t. But so what? That's not a problem. We can just replace the square root of t with t. And these issues really are very trivial indeed. So in any case, it's very natural to consider the Jacobi theta functions. And we can look at the algebra they generate, and we can define a multiple Jacobi value to be any totally critical value of the multiple L function of a sequence of R such theta functions. Now, these numbers are going to satisfy an incredible set of identities. First of all, the theta functions alone satisfy extraordinary identities that have been explored throughout the ages. The L functions even more so. In particular, we already know, because you can actually write modular forms, all modular forms as polynomials in theta functions. This is going to contain all the previous examples we looked at, namely the case of modular forms and the case of the Riemann multiple psi function. And by Sard's theorem, we know that multiple zeta values occurred as in the first example, as where the theta I were Eisenstein series. So this is a vast generalization of the last two examples. But the multiple zeta values occur in a completely different way as well, which I think is quite striking. If you take theta 3 to the 4, there's this particular combination of Jacobi thetas, you get a pair of incredibly simple weight 2 theta functions that I call theta plus and theta minus. And they satisfy this functional equation and this functional equation with a minus for minus and a plus for plus. And their L functions now have the nice property that it relates S and 2 minus S. And the reason that's nice is because now you have a very natural point at which you can evaluate them, namely S equals 1, which is slap in the middle of the functional equation. And in fact, if you would to try to cook up an L function which satisfies this functional equation and has no pole at S equals 1, This is basically the simplest possible thing you can do. So you have a very natural pair of theta functions, plus and minus. And if you consider the multiple, the mixed L functions associated to them, they have a unique central point, 1, 1, 1, 1, 1, which is completely symmetric with respect to the function equation. And if you evaluate these numbers at that point, you find, miraculously, that you get exactly multiple zeta values and log of 2. These multiple Jacobi values are going to contain multiple zeta values in two completely different ways. The first, Varsard's theorem of our modular forms in some subtle way, and here in quite a direct way, using the fact that P1 minus 3 points can be uniformized using these theta functions. So these multiple Jacobi functions, multiple Jacobi values contain, they see the geometry of the moduli space M04, P1 minus 3 points. That's this theorem. But they also capture everything to do with M11, so genus 0 and genus 1. And that's why I think that if you do, if someone does choose to explore these numbers, I promise you, you will not be disappointed. There'll be all sorts of theorems that will fall into your lap. And I think it will be very connected to some of the themes of this conference because it speaks to genus 0 and genus 1. Good. So now I'm going to switch topic momentarily. So I discussed classical L functions and defined some multiple version of them. Now I'm going to do something different. So to motivate this, let's just flick back. So Hecker, what did Hecker do? Hecker, who was just thinking about modular forms, of course. Sorry. Here we are. So Hecker took a modular form and he wrote down a Dirichlet series, this one, and realized that the modularity of F, namely the symmetry with respect to tau goes to minus 1 over tau, gives this functional equation on the L function. And his definition, the recipe to get the function lambda from F was, here it was, is basically a Mellin transform. So we can do the same thing, but we can try this with not a holomorphic modular form, but we could try this with a real analytic modular form. Okay, so this is a priori something completely different. And the relevance to this conference is that you could take a modular graph function that occur in genus 1 string perturbation theory, about which we've heard many talks. Or you could take a modular graph form, and that's going to give you an L function. Okay, so let's do it. We can take, in fact, any real analytic modular form and try this idea. So for me, a real analytic modular form is a function from the upper half plane to complex numbers that is real analytic, and it has modular but with two weights, W and W prime. So if you apply a modular transformation, Möbius transformation, then you get back the same function, but multiplied by a holomorphic automorphy factor, C tau plus D to the W. So this is very familiar from the classical theory of modular forms. But what's new is this anti-holomorphic transformation factor, C tau bar plus D to the W prime. I also want it to have an expansion. So people sometimes call this a Fourier expansion. I don't know why. It's strictly speaking not a Fourier expansion, but I may lapse and call these coefficients Fourier coefficients. I think we tend to think of them as kind of generalized Fourier coefficients. But the expansion is that it's a polynomial, so it has a finite number of terms of some power of the imaginary part of Z times some power series. So a two-dimensional power series in Q and Q bar. So a classical holomorphic modular form would have no Q-bar dependence, and we wouldn't allow any powers of any imaginary parts of Z here. Okay, so the summation range for K is finite, but the M and the N's go off to infinity. And I need a very, very weak condition on the coefficients that they don't grow too fast. So these conditions are amply satisfied for modular graph forms. Yeah, that's certainly known. So modular graph forms, modular graph functions are certainly examples of such functions. So so what we do is take these coefficients, and we can, so for each K, we can package them into a Dirichlet series. And the funny thing is here about it is that you don't, these L series, there's one for each K. So I remind you, K is, oops, my mouse. K is each term here, each power of MZ. You get one Dirichlet series for each K, and these coefficients A don't all play a role. It's only the sum of them. It's only the sum of AMN such that M plus N is a fixed number that occur. So you lose a whole lot of information when you form this Dirichlet series. And then we can define the completed L function to be a finite sum of some power of pi and some gamma factor times this very explicit Dirichlet series. Okay, so the key point is, does not depend in this formula. Nowhere do you use any of the what are called the zeroth Fourier modes. They simply don't arise in the formula. The L function does not depend on them at all. And in fact, it doesn't really depend very heavily on these Fourier coefficients. It only depends on certain sums of them. This is not a classical L function. It's because it's a sum of Dirichlet. It's got different gamma factors coming in. It certainly doesn't have an Euler product. So a theorem, it's really easy to prove this theorem. So I called it a proposition. I was too embarrassed to call it a theorem. It's stated, it's very easy to prove. It's stated in a paper of mine called a class of non-holomorphic modular forms. It's not in the archive version because it was a bit of an afterthought. So it's in the online version. If you want to look at this, don't look at the archive version of that paper because it's not in there. So the statement is that this L function has a meromorphic continuation to the complex plane, and it satisfies the functional equation. All right, no big surprise there. It also has simple poles with, and the principal part, in fact, gives back exactly all the zeroth Fourier modes. So that's kind of fun because it means that in recalling the definition of the L function, it didn't use the zeroth Fourier modes at all. So this L function gives us a recipe that if we know all the other Fourier coefficients for M n bigger than 1, then we can reconstruct the zeroth Fourier modes by forming the L function and taking its residue. So I think that might be of some use. So here's an example. Let's look at a real analytic Eisenstein series. So E, I like to take it with different powers, W and W prime here. Classically, you take W equal to W prime, but it can be a bit more general. This has modular weights W, W prime, and it turns out that its L function is a product of two Riemann psi functions. And so that explains a lot of stuff because it explains why if you look at the Fourier expansion of a real analytic Eisenstein series, you know that all the Fourier coefficients are rational, but the zero modes are zeta values. And that of course follows from the previous proposition because the zero Fourier modes are just the residues of this psi function, and it has exactly two poles. There's one pole coming from this psi function, there's a pole coming from the other one, and you get an odd zeta value and you get an even zeta value respectively. So it explains precisely where these zero Fourier modes are coming from. So in generally, to any modular graph function then, we can associate a completed L function. And I think it's going to be interesting. I've not tried to compute any. I would be delighted if someone wants to do that. One thing I can say in favor of this is that, in fact, if you apply these Cauchy-Riemann differential operators, like these raising and lowering operators, on these modular graph forms, you get a very nice relation between their L functions. So these L functions reflect the differential structure in a nice way. Okay, so let's wrap it all up. I've defined different types of L functions now in this talk, and it turns out that they're all connected to each other. So the next theorem, so let's take my favorite family of real analytic functions, real analytic modular forms. Actually not so easy to construct, but there's a very canonical supply of real analytic modular forms, and they come from elliptic curves, which is one of the themes of the conference. So how do you do that? Well, you take the universal elliptic curve, E tau, you puncture it, and you consider all iterated integrals on it which are single valued. Okay, so that means you take an iterated integral on your elliptic curve, and we have to be a little bit careful about tangential base points and so on, because we've punctured the curve, but let's not worry about that. This is a very canonical thing to do. So we take, in mathematicians' parlance, we take the pro-unipotent completion of the universal elliptic curve, punctured, and look at its single value periods. So those are numbers, because we've integrated from, around a loop on the curve, if you like. Now, if we now vary the parameter of the elliptic curve, we're going to get functions on the upper half plane. And those are precisely a very special class of real analytic modular forms that I call MIE, which are what's known as what I call equivariant iterated Eisenstein integrals, because you can show that they are iterated Eisenstein integrals which are equivariant, which means modular. So this is the universal, a universal family of such real analytic modular forms coming from elliptic curves. And if you compute the L function of them in this non-standard L function, then you can show that actually what you get back is a mixed L function, as I defined in the first half of the talk, associated to a bunch of holomorphic Eisenstein series, in which you hold all the values S, all S1 up to Sk minus 1, constant, and you only allow the last parameter to vary. So that's yet more evidence that these mixed L functions, at least in this modular case, are doing something really interesting. So if you like, from this theorem, we get a prediction. If you have any modular graph function and compute its L function in the way I explained, then that is going to be a linear combination of these mixed L functions of Eisenstein series. So conclusion, what we did is we started off with the very classical theory of L functions, which goes back many centuries. And by passing through their Mellin transforms, we wrote them as integrals, inverse Mellin transforms. We wrote them as integrals and defined mixed L functions as the iterated Mellin transforms of a bunch of L functions. I should say, I have no idea whether this is the right thing to do. If you take motives of rank 4 or higher rank, I have no idea whether for R bigger than 1, this is the right object or not. That's why I'm very cautious. But I think this is a first step in the right direction, because as we've seen, these functions satisfy many nice properties. And in the case where the underlying L functions are rank 1 or rank 2, they're totally critical values connected to many very interesting periods. They related to string amplitudes, as I mentioned, to elliptic iterated integrals on the previous slide. They relate to modular forms, they relate to lattice sums, and they relate to many topics which have come up in various talks in this conference. And so the bell has just rung, and this is a perfect place to stop. Thank you very much for your attention.
Yes, thank you very much, Francis, for this talk. Let's unmute for a moment in order to exert our applause. I'm sure there is a lot of questions for this talk, but before we get to the questions, I would like to take the opportunity to thank all the speakers and all the participants for their talks and contributions to this conference, for the discussions, and for all other help and input. I experienced this conference as a very vibrant and colorful conference, and I hope we somehow managed to understand the respective languages a little better. At this point, we as the organizers would also like to thank Olli C. Sorli and Felix Achtmann in Mainz for their administrative and technical support. In particular, there will be videos of the talks, and they will be published on the MITP, that is the Mainz Institute of Theoretical Physics, YouTube channel in the very near future. So far, nothing is online, but it will be so very soon. Okay, so thanks to everybody who made this a very nice week. Now, yeah, this is an online conference. Now we should get back to the questions for Francis. And David Broadhurst has raised his hand. David, please.
So thank you, Francis. My question concerns the first part of your talk. And the big message I picked up there is that we should be critical about our use of the word critical. And that resonates back, if you remember, to 2010, when I was asking you about the magnetic moment of the electron at 4 loops, and later we went to 6 loops, and morally what we should have been doing on the edge of the strip, but we ended up at pi squared times something inside the strip. And then later, Anton Mellet and David Roberts and I showed that you can actually get outside the script and engage with things which Fernando had done. So my question is, can you get outside the critical box?
That's a very good question. I don't know. I don't know anything about values of L functions outside the critical box. Well, and that aren't totally critical in the case where R is bigger than 2. I do know about something outside the box. The Riemann-Xi function, remember, I know something about even, comma, even, and they can be outside the critical box of the functional equation. And that was the motivation to study that. But let me provide you with sort of enhance your question and say, well, you could say to me very fairly, what happened to the non-critical L values in the case R equals 1? Because there's Beilinsen's conjecture. I can't just throw it away. And it turns out that those non-critical values in all these cases show up as totally critical values of a double L function. So everything you had in the classic for classical L function, R equals 1, you have the critical values, and then the non-critical values. All the non-critical stuff shows up as double L functions. And so in fact, you only need to look at the totally critical values. And that's why, so an answer to your question is, I don't know anything about any non-critical values, but I'm not too worried because I haven't thrown anything away.
Okay. There's another question from Lance. Lance, please.
Hey, Francis.
Hi,
thanks for that fascinating introduction to this developing general theory. I was wondering if you can imagine something a little less general. Suppose I want a machine that produces multiple zeta values, but not all of them, but some subset that's closed under a coaction. Is it possible that that could be related to some subring in these theta functions that are associated to it? And you know, similar things in in the larger non-multiple zeta value context, like electron G-2 or phi to the fourth periods?
That's a very good question. I don't know the answer to that. I had nothing particularly intelligent to say about that. So off the top of my head, I would say one thing, that you can, that the normal way we write zeta values is with this indexation n1 up to nr, and the index r is the depth, and the depth is motivic, which means that it's preserved under the coaction. I had a theorem somewhere, if I can, I had a theorem somewhere here, that there was a different way of writing them, as iterated integrals of these theta plus and theta minus. Now, if you translate this back, this means you take not dz over z and dz over 1 minus z, but they're symmetrized and anti-symmetrized versions with respect to z goes to 1 minus z. And you get a new filtration. You can count the number of pluses and number of minuses. And I think that's, I think so. My Adam Kilty, I think, checked that is motivic as well. So you do get some new filtration on multiple zetas, which will be stable under the coaction. So yes, I think that your question is a great question. I'm sure stuff like that is out there, but I don't have anything in mind apart from this very special situation.
Great, thanks a lot.
Yeah, maybe Niels.
Hi, Francis. Good to see you again. Thanks for a great talk.
Hi.
So I think my question is rather ill-defined because I'm asking about something which you haven't really defined in your talk, as you admitted, the mixed L functions. So, but to a mixed motive, you've associated a mixed L function. Can you go the other way? Can you reconstruct the motive from the mixed L function?
Good question. Sort of. So if you, I mean, intrinsic in the definition of the mixed L function is the theta functions, right? So they each correspond to pure motives. So if you've got the constituent pure motives, right, which are the building blocks of your mixed motive, and then you need to glue them together. You need all the extension data. Well, the extension data by Beilinson is encoded by the regulator, which is the value of the L functions. So, and since you know you've been given the values you're evaluating it at, you know something about the extensions as well. So I don't really know the answer to your question, but it's going in that direction. It's heading in that direction.
Okay, thanks very much.
Yeah, Claude, you had a question.
Yeah, hi Francis.
Hi, Claude.
So I've understood correctly, so you started off by saying, well, if I take the classical theory of my L functions, which give me periods, at least if I evaluate them with special points, and I said, well, what about the kind of converse question? So can my periods, could they come from some hypothetical extension of my theory of L functions? And you gave a candidate, and you were very careful to say, well, this may not be the end of the story. But let's assume that this was really the end of the story then. And all these things that you defined were iterated integrals.
Yes.
Would it mean, would that have some implication? For example, what about things like, I know, let's say a complete elliptic integral, which are some periods, but which I would not naturally see as an iterated integral of some sort, or what would that imply? So usually I think of these things as certain things which are like iterated integrals and certain things which are not, which may not be the right way to think about it. Well, what you said now is, well, if this was the right picture, they would all be iterated integrals of some sort.
Yeah, so I'll say two things in response to that. First of all, if this were the right picture, things go a bit weird in higher rank, and that's what makes me nervous. In the case of rank 1, the zeta theta function, so the Riemann zeta function, we got a Jacobi theta function. So that's not a very algebraic thing. It's something. It's not a very nice algebraic object. In the case of cusp forms, those Hecker eigen modular forms can be viewed as something algebraic. So we get iterated integrals of something that looks algebraic. They're kind of periods. if you start with a higher rank motive, a rank 4 motive, these theta functions are not algebraic at all. They look scary. They've got sort of Bessel functions and stuff. They've got Fourier expansions involving weird Bessel functions. So an iterated integral of those would not, in any obvious way, be an iterated integral of something algebraic. So perhaps these examples are slightly misleading in that respect. But the other thing I would say is that in some sense, there is a sort of very philosophical sense, but well, there's a technical sense in which all periods are iterated integrals of something. And the reason for that is because this is very technical, but there's a way to construct mixed motives as the bar construction on a cycle complex of something that computes K-theory. So what that means is that mixed motives should be something like iterated integrals on something which computes pure motives. And if Bennington is right, there's something that computes pure motives is the L function. So it has to be the case, I'm sure it's the case, that all periods of mixed motives are somehow iterated integrals of something. The question is there something that I've written down the right one?
Sure.
And in the case of, as I've said, in higher rank, rank 4 and above, I'm nervous, which is why I'm cautious. But even a single example would be fantastic to either refute or confirm. So that's what the answer is sort of yes and no, if that makes much sense.
Okay, no, I think that that answers the question at least. I mean, I don't know the details of what you said, but when you say, okay, there is something like a bar construction that should also do these things, I can live with that, yes.
Yes. Are there more questions from the audience? No? If that's not the case, then let's thank Francis again and unmute again. Yes, and the Zoom room will be open for a little longer for those who want to stay, but that is the official end of the Elliptics and Beyond Conference 2020. Thanks again all for coming and contributing, and thanks for all the talks.